Thank you. I'm going to let my friend Alex present first.
I'll get this. Okay. Cool. Is it working? Excellent. Good afternoon, everybody. Alex and Daniel, glad to be here. Thank you very much to droidCon organizers for inviting us. Today we're going to be talking about building good apps on bad networks and low-end devices. And you may ask yourself, who are these people and what do they know about the subject? Well, we've been working on stuff related to the subject for, between ourselves, probably close to 10 years. In companies like Microsoft, Facebook, and Google. At the present time, neither of us is directly involved with this particular subject, but it's very near and dear to our hearts, and we think there is stuff here which would be interesting to everybody as well from our experience. I was mostly involved with this in Facebook, first as an engineering manager for the emerging markets team, which we started at Facebook to make sure the Facebook app works really well on bad connections and on bad devices. And then as a product manager for a brand new app at Facebook, which was called Messenger Lite, and it's still out there. And it's a Messenger app optimized for that space. Now I work at Lyft. Lyft is an American company. It's a rider-share company. It's operating on American networks, uses American devices. But I'm finding that a lot of the principles and a lot of the problems still apply. So again, I think it's going to be interesting for a broader audience as well. It's a little bit delayed. So why worry about bad networks? I'm going to start talking about the networks, and then Daniel is going to talk about devices. That's how we're going to break this up. So in emerging markets, the problem is pretty obvious, just like an example that Maria gave at the beginning. Congestion is a fact of life. Bad networks is a fact of life. Things are improving in emerging markets, but they improve pretty slowly and not necessarily linearly. As a part of our job at Facebook, we used to go all over the world, trying out, seeing different connections, seeing how we can improve, and we went to India quite a bit. And India provided this interesting experience. We were going to the same place in Hyderabad, over a period of about 6 months. And first, the connections were really bad, and then the connections become quite good because, things are improving, the new cell phone towers go up, and we were actually a little bit disappointed the second time because it was kind of hard to test in the area we were in because everything worked so well. And then 6 months later, we got there, and the connections are bad again. So what's going on? We asked Airtel, which is one of the biggest providers over there, and they said, well, there is this office tower just went right by you, and that's another 2,000 people, and it's again congested. We need to put another tower in there. In places like Bangalore and Hyderabad, they change so quickly, and so many people go online, even when things improve, it's not a linear improvement. It's up and down. So I think the bad connections are going to be with us in emerging markets for quite a bit, even though things are improving overall. But what about places which are not emerging markets, places like Germany and US? I think everybody here probably had some experience with bad connections. Actually, can I see a show of hands, people who had some experience with bad connections in some time? Exactly, right? I mean, you got a couple of different situations here. One is a temporary congestion. Like a conference like this, it's crowded, everybody's on the cell phone, Wi-Fi may not be good. All of a sudden, you got the situations here. Concerts is another good example. You're traveling, you're going for some patch which doesn't have connectivity. The other problem is physical barriers. Like if you're on a subway, if you're on a plane, if you're in some old building which uses materials which are not conducive to cell signal, I mean, you run into situations all the time. So again, these principles apply in many different cases. Yep. So the first thing that everybody learns when they start working on optimizing their connectivity is that bandwidth is a valuable resource and it should be used sparingly. And again, the very first thing that just about everybody does who works in the space is looks at media, looks at images, looks at videos, and tries to think about how you can lower the resolution of this for their case. Because there's no point actually showing high-profile images. If it takes so long, nobody's going to actually see them. You won't be able to download them. Most of the time, it's a little bit of a trade-off, right? Because if you're showing better images, you have better experience. Sometimes it's not actually even a trade-off. When we just started doing this work at Facebook in 2014, 13, 14, we realized we're downloading images which are so big that most of the phones that were in emerging markets at the time, actually in most markets at the time, the screen was much smaller than the quality of the image we download. So we can just reduce the resolution and nobody would even notice. That saved a bunch of space, and then this optimization become sort of void 2 years later because Android screens just become much bigger, and all of a sudden that that's no longer applies. Then the next thing that people can think about is actually the design of the app. Often the design of the app is actually thinking about the network connectivity in the design of the app helps quite a bit. One of the things that Facebook Lite did, which is a light version of the Facebook, is that they reduced the number of images they show in the newsfeed from 5 to 3, and then they also made the images smaller. because they felt that for the users over there, it's more important to be able to download connections, those images faster and use less data, and then it turned out to be right. Actually, user response was more positive when you give them smaller images and you give them fewer of them, because they could still see what the news story is and you can still get engaged with that. The other approach that, for example, WhatsApp tried, and it worked really well for them, is to show blurry images. So drop the resolution, show a blurry image when you embed connections, ask the user if they want to see this image or not. WhatsApp had this feature from almost the very beginning. It's very, very popular for them. Again, Messenger versus Newsfeed, it's a little bit different. In the Newsfeed, if you do that, you actually, the stories being interesting depends so much on the quality of the image that most of the time people just say, oh, the story is not interesting because the image is so bad. But in Messenger situations, I mean, it works really well because typically you know what you're getting. You want to see it or you don't want to see it depending on the content, and you can decide whether you want to do that or not. The other kind of trick that you can use here, and this is the one that Instagram used in 2014, is look at some of the images that you commonly use in the app. For example, icons. And think about, do you actually have to download images for them? Or can you generate this on the fly, just programmatically, right? So Instagram actually went and redesigned all of the images like that, all of the sort of icons, to make sure they can generate most of them on the fly. And this way, they don't actually have to download anything. They will just build them on the fly, and that's worked really well for them. Finally, when you talk about the images, image formats. Image formats are actually very important, and they could really make or break the size of the images that you download. In, again, 2014, 2015, we switched in Facebook from JPEG to WebP format, and we saved about 40% of our space by doing that. But then, as we started learning more and more about the formats, we actually went back to JPEG. It turned out that by tuning the JPEG parameters, we can do as well as WebP, and then JPEG gave us one extra thing we could do, and that's downloading the images progressively. Progressively means you download a few scans of the image, and then you refine as more and more data comes back from the server. Why is this so important? Well, I mean, studies show that on average, a user would wait about 3 seconds for a blank image before they moved on to doing something else. This is pretty universal. Different companies did the studies. It doesn't matter what network you have. 3 seconds is all people are going to wait. On a 2G connection, I mean, it takes about 2 seconds to establish the connection in some of the cases. So it's important to get the user something very quickly so they can actually believe that the image is going to come through. So progressive rendering became pretty useful for us. Now, if you are doing it in your own app, of course, I mean, this is pretty complicated. How do you figure out what format to use? How do you build progressive? So my recommendation here would be just to use one of the image libraries. Most people use them anyway, and just choose them carefully. A lot of them optimize with the right format. I think Picasa uses WebP internally. If you want progressive rendering, Fresco is the Facebook open source library that you can use. And then this problem gets fixed for you there. Fetching once. Everything that can be reused should be cached. Everything that has a high probability of being reused should be cached. And of course, it's most important for media, for images, for videos. And caching becomes really important. In general, the way we do the caches is that we've allocate some size for them, and that size could depend on your device. If your device doesn't have a lot of memory, you sort of don't have much choice, right? You just utilize as much memory as you can. You can't really tune it very well. If your device has enough memory, use it. A good way to do this is just test it, try different sizes, see if they have an impact on your performance and like your user experience. At some point, you'll find that providing more size doesn't really matter, and then you can cut it off right there. The other thing, again, is prefetching data. Again, remember that story about 3 seconds, right? 2 seconds to establish the connections. You might not be able to get anything there. So you would be showing blank images. Users will be scrolling past them. That's not good. So prefetching data, which has a high likelihood of being used, is pretty much a must in these situations. Of course, you need to know that there's a high likelihood of this data being used, which newsfeed stories, images, sort of pretty likely. In some other cases, you can get away with things like prefetching on Wi-Fi, so you can actually start fetching ahead on Wi-Fi because it's pretty cheap to get stuff there, and it's usually pretty good connection, and then you can show it later. In Facebook scenario, we would prefetch newsfeed images, and we will prefetch them ahead of time. So you would be looking at the story, and we will be fetching images for stories which are farther down as you scroll. And the worse your connection is, the farther down we will actually look. For some of the worst connection, we would look at as many as 10 stories ahead to start prefetching these images, just because it takes so long to get them. That actually worked really well. And images were there when you actually needed them. They were in the process of loading at the time, and that had a pretty good impact. This is all a trade-off, right? You got your size trade-off, you got your bandwidth trade-off. If you fetch images which you don't reuse, or you prefetch images rather that you don't use, you're wasting the bandwidth instead of optimizing it. So just think it's a pretty complex system. So do monitor things around that, right? Monitor how often you evict things and then you use them. Monitor how often you actually don't use the images that you put in the cache. Look at all those different things because you'll have to look at the specific scenario and balance your trade-offs. There was a talk here yesterday, I think in a Turing room, about designing optimistically for pessimistic world, I think it was called. And it was great. It had a lot of the thoughts that I was about to talk to for this slide. And that's about how you design your UX experience in a way that you don't assume that the connection is there. So you always write to disk, you always read from disk, and then what you do is you synchronize your network data asynchronously, right? This really works great, and it's a fantastic thing that all of Facebook apps use quite a bit, and all other apps use as well. The one case which presents additional challenge is a startup case. You never want to show a blank screen on the startup. Sometimes it's unavoidable, like you have a login sequence and you have to go through the login sequence. The network has to be there for that to happen. But other times it's actually avoidable, and you can actually do something useful even before you hit the network for the first time on the startup. For Lift app, for example, what we do that with a map. When you boot up the app, it shows you the map from the last time when the app was booted. So if you are in the same location, that's fantastic. You already have the map ready to go. If you're not in the same location, you understand why you're seeing this, right? Because it came from the last time, and it gives you a little bit more time to do something while we're loading the map. What proved even more effective is caching all the popular destinations. When you call a car, a lot of the times it's the same destination. It's work, it's home. So caching these destinations allows you to start the process of ordering your ride even when the network is not available for a few seconds. Obviously, eventually it will have to be available for this to work, but it does help you with the actual experience and not being blocked by the network at all.
I just want to add that during startup, you want to overlap as many different kinds of work as you can. So if you are going to create a network connection to service some sort of user request anyway, start it as early as you can during application startup so that the network connection can proceed while the application loads code, decodes images, things like that.
Yep, yeah, very true. And so what can you do in cases when you have a lot of intermittency in the app? Well, the one thing you want to do is make sure the app keeps chugging along and working, right? So you can survive this intermittency periods in the app. This leads to basically making your clients smarter. The clients need to know enough to be able to continue to work even the network is not there. It also means saving enough state on the clients that they can do that. Again, ride-share apps do a lot of that, especially on the driver side. Like when the connection drops, we want the driver to be able to actually get paid for the whole ride. So we don't want to just terminate the ride the moment the connection dropped, right? So we store a lot of data on the client so we can continue chugging along and survive periods of connectivity. Another thing you can do here is actually, again, use your product design and think about this and think about situations more. Again, one example from Lyft's experience, in a lot of airports, cities require drivers to wait in line and only have a certain percentage of the drivers go one after the other. And so there are a lot of drivers, potentially 100, 150 drivers just waiting in line for their turn. And they all have their phones off, and that leads to congestion. That often leads to congestion, their connection can drop, and nobody wants to be going in the back of the queue when it takes you 30, 45 seconds to get to the front of the queue, right? Just because your connections have dropped. So the way we decided to actually address this is just to give you 5 minutes outside of the lot, kind of a grace period, so you can come back. So there are other scenarios in which that might be useful, but the driving force here was really network connectivity, because we knew that's happening. So when the connection drops, or say connection drops, or you're out of the lot, and then the timer starts. Again, if you don't have connectivity for more than 5 minutes, there's nothing we can do. But that just dropped the number of requests, the number of complaints about this dramatically, because this was basically sufficient to make sure this works. The other thing is just thinking hard about the situations where your app is offline for prolonged periods of time. There are actually a lot of apps that work really well offline. Apps which show movies, which are cached on the device, play music, which is cached on the device, play games. All of this stuff is great, and it works because the content is there, and you can use that. For an app like Facebook or Messenger, we actually had to think about how do we make the app useful when it's offline. in Messenger case, we basically keep the threads around. Like we have, up to a certain time, all your threads are there. You can still engage with them and read about them and respond to them as well. In the newsfeed case, what we do is we actually have a lot of stories which you haven't seen prefetched when you do have connections, right? We always make sure that there is some number of stories which are there, which you haven't seen before. And then we went one step further as we said, hey, we can rank the stories because we have quite a few of them. So we shared the code from the server to the client so we can do some basic ranking. And so what happens then is if you don't have connectivity, we can still show you new stories, rank in a proper order, so it looks like the app's still alive and you're still getting new stories. It also works really well in the bad performance cases because if it takes you a while to get to the new story, we start injecting these all stories, which you haven't seen before, while continuing to load the stories so we can put them next when you scroll down. And this leads to the feedback from the users was like, this is magic. Like I'm on, oh. But this is magic. I am on this bad connection, and I still, when I go for the stories, I still get to see something new. So that worked really well. Oh, good. Okay, now let's talk about how you actually use the networks in this situation. Because usually when you're in intermittent situations with bad connectivity, you have the small windows when the connection is available, and you want to use them wisely. So I'll start with the DNS resolution, which is sort of a trick that I think WhatsApp started doing first, and that worked really, really well for them. So DNS resolution is, for those who don't know, that takes an address like live.com and converts it to IP, and IP is what you need to be able to communicate with the server, right? Pretty straightforward. DNS resolution is one of the first things that breaks in these situations because resolving DNSs takes multiple hops. And so when the network goes down, there's a very high chance that one of these hops is going to go down and the whole operation is going to time out. Fortunately, there is a way to deal with that. And this way is to basically cache the results of the previous DNS resolution and fall back to that if your DNS resolution fails. This is precisely what WhatsApp did. And for a while, when we went to India, there was this, again, magical thing where no app would work, but WhatsApp would work. And the user would say, WhatsApp is the only one that works in 2G. And that was true, but mostly because of the DNS resolution. And so, we copied this on all the different Facebook apps, and it's a very effective way to deal with the situations. The other problem is, again, those windows are very small, windows of network connectivity. And you want to make sure you wake up the app as soon as possible when you have network connectivity. Android now makes it really, really easy with Job Scheduler, which you actually have to use to schedule your asynchronous operations with some versions of Android, because the Job Scheduler can be configured to wake up and redo your operation when the network becomes available. And it's optimized for doing this quickly. The alternative approach is, if you can do this, is to switch from polling to pushing. Right? When the server pushes the data to the client instead of the client asking for the data, again, Android optimized pushes to make sure they can use very small windows of connectivity on the client to wake up the app and have it respond to that push, and then you can try to do your fetches and try to do other things in response to that. Then, the app is woken up, you have this connectivity, how do you actually use that space and this opportunity wisely? If you upload something which is a big file, big batch of data on the server, there's a high likelihood that the window is going to close and you're not going to succeed uploading this, right? So it's generally a good idea to upload things in small chunks as much as possible. On the flip side, when you download things, it's generally a good idea to organize your APIs and your flow in such a way that you download the most important data first. And again, it's really useful here to work with your app designers and think about, can I move some of this data, which is not critical, off the first screen so I can show it later, or I can show it on demand. This is one of the reasons why in Facebook we show comments one click away from the actual story, because comments are expensive to get, and we want to make sure user really wants to get them before we download them. In the meantime, we can download the core part of the story without having to depend on downloading these big batches fully to show you a good experience. And finally, this is a little harder to do, in a kind of a small shop and for individual developers. But using a single connection is something that's really helpful. Usually in Android, when you spin another network request, you're going to have another connection. Multiplexing between this connection actually doesn't help. You remember the story about the 2G being this, taking about 2 seconds to start up a connection. You pay for that pretty dearly. If you can optimize it so you can actually use a single connection to the server and then multiplex your operations on it, that actually has a pretty dramatic effect in some cases. Facebook Lite is an app that uses it really well, and now Facebook also does this, but in cases with really bad connectivity. It basically tries to get everything on the server and then open the single connection for the data, so you can do both images and text through the same connection, and improves performance quite dramatically. Knowing your user, again, this is all a trade-off. In all of the situations, I mean, you're optimizing for your data, you're optimizing for your connectivity, you're optimizing at the cost of something else. Very, very important to know who your users are and what their problems are and how they segment between all these different categories. The big thing to do here is, of course, analytics. You want to report back. You want to report back things like, what are the qualities of my network right now? What are the qualities of my device right now? You want to compare the results and see what problems the users have when they have these problems. One thing about analytics is a kind of caveat. Most analytics libraries, people or apps that use analytics, they do the proper thing. They store things on the disk, then they send it, then they try to repeat if the network is not available. Unfortunately, if the network is not available for a long period of time, they can start running out of disk space. There might be some other failures. So there's a pretty fair loss in situations where you're offline. So when you interpret your analytics, interpret it wisely, because you're probably not getting all the data from users who are network constrained, or you're getting less data from them than you do from users who are not network constrained. So one anecdote over here is, for a while, we had very few bug reports in Facebook from users who were network constrained. And we don't know what to do about this or how to think about this. I think the prevailing theory was that they just don't use the app as much because they're network constrained. Well, what it turned out to be is that the bug report flow was blocked on getting to the networks, so at the very beginning of the flow. And so, of course, they would not be reporting these bugs because they can report them when there is no connectivity, right? So removing this and making sure we design the process in such a way that they can report even when they don't have the connections, and then we rely on analytics and retrying to get this through, improve this dramatically. We started getting more bugs, which is probably the only time in my professional experience I actually liked the fact that we suddenly got a lot more bugs for that space. But it's something to think about. The other thing to think about is knowing the environment in which your app is running, and then programmatically targeting your experience in the app to the right capabilities of the device. So here, there are actually multiple open source libraries out there that tell you about the quality of the device that you run on, or the quality of the network that you're currently experiencing, right? Facebook had a couple of these things open source. One was device class library, and the other one was network connectivity library. They can be used, and then you can sort of target your experience to these situations. So you can sort of decide what you're going to do in these cases. Like I said, it's both the UI and the infrastructure that you can target. And if you're starting to target a lot of the UI start changing for users, right? I mean, it's like big pictures, small pictures, depending on their connectivity, is probably not a very good idea. So you should start considering things like modes. Saying, hey, I mean, should we put users explicitly in a different mode? Or should we request that they put themselves explicitly in a different mode so we can give them these optimizations? This is things like offline mode. This is things like low data mode. Facebook has a low data mode now, where you can just say, hey, optimize for data at the expense of all these other things. Some of them would be experience, some of them would be space, but it's a good resolution for this issue as well. And with that, I'm going to pass it on to Daniel to talk about the devices.
Hi, I'm Daniel Colascione. Just want to tell you a little bit about myself first. I've been doing systems programming for the past 7 years or so. I've started on Windows Phone on the fundamentals group, spent about 3 years there, spent just shy of 3 years at Facebook working on low-level Android application infrastructure, lots of ARM assembly and NDK work. And now I'm at Google on the Android performance team. Before I say anything else, I just want to clarify that I'm here in my personal capacity, so don't interpret anything I say as any official endorsement or anything. Next, I'll just tell you a bit about the segment of the talk I'm going to give. It's a bit different from typical talks. First of all, there is absolutely no Kotlin in it, and I'm not going to talk about a new framework. Is this better? Awesome. OK. Oh, I need the switcher. Thank you. Systems programming is fantastic because it's really the underpinnings of everything else in terms of application logic, network connectivity. It makes you feel like a black magic wizard. And mobile systems programming in particular is great because of the constraints. It's like writing a poem in a way. I mean, you can write free verse and just stick anything you want on a page, but if you're writing a sonnet, there are sort of forms you need to fit into, and those forms really spur creativity. It's fun. Low-end devices are even more fun in that respect because all the problems of normal Android devices, things like fragmentation, system resource contention, just sheer age and wearing of device storage, these things are all amplified. So it's a bit of a challenge. I'm going to give you a few recommendations I've derived over the years about how to effectively deal with a diversity of devices of various qualities, and then I'll give you a couple war stories that sort of have used these themes that I've developed to achieve performance gains that wouldn't have been possible with purely conventional approaches. Performance involves making the best use of the available system resources. You have a certain amount of compute, you have a certain amount of memory for caching, you have a certain amount of memory bandwidth, and you want to, as much as possible, make full use of these resources simultaneously, overlap as many different kinds of work as possible, and understand the extent to which these resources affect each other. In many cases, particularly space, speed, and size all interact. And when you optimize one at a time, you frequently pessimize some of the others. It's also important to verify the assumptions that you're making about the system. And I'll get into this a little bit later, some techniques for doing that. But the basic idea is that human beings are very bad at estimating where bottlenecks occur. I mean, research study after research study shows that if you ask programmers to point out the bottlenecks in a program, bottlenecks will have very little to do with where the bottlenecks actually are. You need tools and profilers and things like that. Anyway, I need to hurry up. So, okay, first recommendation for dealing with low-end Android systems. And this is something you need to do on Android systems generally, but on systems with limited memory, it becomes more important. The system is allowed to kill your process at any time for any reason. The SDK documentation say things like activities in this phase of the life cycle are killable, and no, it's not true. What's true, the system will prioritize applications differently depending on what they're doing, but you need to make sure that everything you do is atomic and consistent, and that you can reason about what happens in your application when it's killed at any moment. And I'll get into later a little bit about how you can tell what's going on. The next thing I want to mention is crash analytics. Particularly when you try to massage the framework to do certain things you wouldn't do otherwise, or you want to run a large diversity of devices, you encounter basically every single problem that Android has ever had. Another speaker today mentioned that you're basically exhaustively searching the space of bugs once you have sufficient scale. So being able to analyze those is really important. One thing I found critical is obtaining not just stack snapshots when something goes wrong, but also full state dumps of the application. You could actually run logcat as a subprocess and extract a part of the ring buffer, the logcat ring buffer relevant to your application. You could do things like list files and directories. For example, one time I was at Facebook and we were deploying an application to this new device. And the makers were very proud of it. They'd extensively modified Android, but it had this bug where if embedded in the APK, a shared library is exactly 63 characters long, it would just skip that when extracting. So loading that library later would fail, and it seemed to be impossible. Another possibility was Android Lollipop had a bug in art and random method generation where you'd occasionally just call the wrong method. Debugging that was fun. Another recommendation is to benchmark your code, validate your assumptions. I recommend using Google Calibre for this. It is a tool from Google that repeatedly runs a small section of code to iron out all the sources of variance possible. And it can tell you a bit about about the implications of specific small pieces of code. Simplicity and beauty, and they sound like really fuzzy abstractions, but there is a correlation between maintainability, readability, and performance. I personally tend to avoid excessive architecture when possible. But at the same time, a program's performance isn't a linear combination of the performance of all its functions. There are resources that are contended across all the various aspects of the program. Things like a process-wide memory map semaphore that you take on every page fault, that you take when you call memmap. There are I/O bottlenecks and so on. So you have to understand how different optimizations interact with others and understand holistically the operation of the system. So, I mean, of course, do benchmark your program. If you're unsure how expensive an operation is, micro-benchmark it. But at the same time, put it into a broader context. One of my favorite stories here is a coworker used to tell us on Dalvik machines, which have a stop-the-world garbage collector, which is non-generational. Linked list append actually turned out to be quadratic in time, not linear as you'd expect, because eventually you'd have to allocate new nodes, scan the entire heap, and so on. And these things can surprise you. Another recommendation I have is to look at the system. I remember programming in the 1980s and having to look at disassemblies of kernel 32.dll, trying to understand what that system was doing. Here, we're lucky enough to have full source code for the kernel, for the framework, for the Java runtime. So you have all the information you need to understand how the system works. I would strongly encourage you not only read the source code, but do custom builds of Android, insert custom instrumentation if you're unsure how something works. This is particularly important when you're dealing with an older device, right? Say it's a used device or something, and you encounter a bug in the system or the framework. Having a thorough understanding of how it works can help you find workarounds much faster than just sort of poking at the thing as a blind box, as a black box rather. All right, 3 examples of situations where we were able to obtain significant performance wins through a holistic and deep understanding of the system. The first has to do with older devices, pre-Lollipop, method verification. Very briefly, on those devices, when you installed an application, it came with a DEX file. DEX file contains the code of your program. Runtime doesn't actually run DEX files, it runs ODEX files, and the runtime during installation transforms DEX files to ODEX files. Part of this transformation involves running a verification pass against each of the classes in the DEX file. And during this verification pass, we do things like make sure that the bytecode corresponds to the bytecode spec and so on. But something else we do is make sure that a code adheres to certain structural constraints. Does anyone see anything wrong with this piece of code? Okay. Or how about why this code might be a bit better? Okay, the answer is that, going back here for a second, we don't actually call from foo the new framework method here. We abstract out to a separate class. The way this helps is that here, when Dalvik verifies foo, it sees a call to a method that doesn't exist and basically throws its hands up in the air and says, hey, I can't verify foo. I have no idea what that is. So in the ODEX files, it leaves it non-pre-verified, which means that at load time, it has to perform an expensive verification pass against all the methods in foo, page them all in from disks, and do some CPU-intensive register value tracking and things like that. But here, it can take foo, pre-verify the whole thing because the verification only takes into account calls that actually exist in that class. And then, in Lollipop compat, you have 2 cases. Either you're running on a Lollipop device or newer, in which case Lollipop compat itself will pass verification because it's calling a function that exists, or you're running on a down-level OS, and since you are not actually calling Lollipop compat do something, and that class never gets loaded, so the fact that it fails pre-verification doesn't actually hurt you. On an individual basis, failing pre-verification doesn't really cause that much of a startup penalty, but once you have a few hundred or a few thousand of these, your application startup just gets mysteriously slow and you have no idea why unless you understand the details of the runtime's operation. And use dex dump and oat dump and tools like that to actually inspect the code the runtime is generating for you. Don't just trust it. I mean, or their trust but verify, I guess. The second war story is the Redux project at Facebook. It is an APK optimizer. You take APKs as input, produces better APKs as output. It works through essentially 2 techniques. First, it rearranges the code inside the APK so that the startup code is contiguous, and so we can load it to memory during startup with fewer I/O operations. The second thing it does is delete unused sections of code. Say we have a Java class with a static initializer, and that initializer just sets a static field to 0. Well, you don't need that piece of code. The runtime guarantees it's going to be 0. There's no point in running it. There's no point in storing it in index files. No point in paging it during startup. It sounds like a small win, but in aggregate, reducing the reference set of the application during startup really helps performance. The tool is open source, by the way. You can take a look at it. And these days, the tool is both more complex in that it does quite a few more sophisticated optimizations. And there are other tools that perform similar work. The third story I wanted to tell is more recent. I was on a team recently that wrote a tool that pushed applications to devices and started them up as part of the edit, test, debug cycle. And users were complaining that these applications took a good 20 seconds to start every time you would make a modification and push them to device. The reason for that was that on devices between Lollipop and Marshmallow inclusive, you would have to compile the application eagerly to native code. That was the art model. Turns out that there's a way to force the use of the interpreter instead. And we're going to push back saying the interpreter will be slow and so on. But if you understand what it's actually doing, that most of the time the application is just orchestrating the invocation of framework and native code, it doesn't end up being that bad, and you avoid the eager compilation overhead. It's not necessarily a good idea to do this all the time in a specific situation. It was the right thing to do. My point is that by understanding the low-level options and the execution model, you can make improvements that you would never gain from just looking at a profiler and tightening up some loops somewhere. You're making better use of the system resource as a whole by using it in a different way. That's it for me. So we're going to do a brief Q&A if we still have time.